Alright, hello, and welcome to our digital walkthrough of the magnetism notes and a couple practice problems as well. So magnetism, compared to electricity, is relatively straightforward. This is something a lot of us do actually have a little bit of experience with. I'm sure a lot of us, when we were younger, and even possibly still now, you play around with magnets from time to time if you have them. You'll try to push them together, you can feel them repelling away from each other. This is what we're going to look into today. How do these magnets work, and how can we calculate the forces on them? So, I don't think I need to introduce magnetism too much. All of us have some kind of intrinsic understanding of what that is. So, here are some examples of how useful and used around the house magnets are in places that you wouldn't even expect. We got things like stereo speakers, we have TV degaussing coils, power supply transformers, just lots and lots of things, components of electronics everywhere around the house. Magnets are used. They do lots of different things. They help control how electricity flows. They can generate electricity. Magnets are extremely useful. It's why we use them so often, even in places where you wouldn't expect, like within TVs, or in places that you do expect, like your refrigerator door ceiling glows with magnets. That makes sense. So, let's go into a little more detail about these. So, magnets essentially have poles. There's a north end and a south end, which I'm sure a lot of us are familiar with. Generally, north attracts south, south attracts north. These are just given by definition. One side doesn't necessarily need to be called north, it's just called that because that's what we've agreed to call it, essentially. North would attract south, south attracts north. Opposites attract like repels, just like with electricity. So north would repel north, south would repel south. And if you ever try to put the same side of two magnets together, they push away from each other because they're repelling. And this is actually something you can feel, which is useful for us. But otherwise, this is very straightforward. Nothing too out of the ordinary with magnetism. So just another quick example, that like poles would repel. If you have two south sides toward each other, they're going to repel away from each other. So that one that's on that rope that can swivel, that south side is going to repel away from that other south side, pulling the north side back towards it so that it would pull towards each other and they would attract. Just like we would expect. So, there is a little quirk to this, and I'm sure some people have thought about this before. If you have a magnet and you were to cut it in half, could you just have a north magnet and a south magnet separately? The answer to that is no. You cannot just split a magnet up and only have a north side and only have a south side. There will always be a north and a south side to every magnet. And that has to do with how these magnets are actually created, how they're actually formed. And this, essentially the way all these different magnets work, at least with solid magnets like bar magnets, fridge magnets, things that most of us have experience with, is within these magnets, all of the atoms essentially are arranged in such a way that most of the electrons are on one side, the positive side's on the other side, is a way to think about it. And they arrange themselves in these kind of lattices, these like crystal structures, essentially. So that when you split it up, you're going to have essentially positive, negative, back to back. And we have a slide showing that. Doesn't matter how many times you split it up. So we can split this first one up into two parts. Now we have two magnets with a north and a south. If we split both of those ones in half, we still have a north and a south. Okay, so a little bit later we'll have it, but essentially within a magnet, you would have positive side like this, positive side like this, positive, negative like that. So this side here, the north side would be positive, the south side would be our negative. So when we split this down the middle, right down like this, you can see that we have positive, negative. Now on this split, we're left with a negative right here. So now we have a southern negative side after we've cut it in half. That's essentially what's going on with this. Let's get rid of some of this. All right. So, another thing that we know about magnetism, some of us, we have compasses. The way those work is they point the way to north. The thing that's a little bit weird about this currently is the way they're set up is magnets don't point towards magnetic north. they point towards magnetic south, because the way the magnetic field for Earth is set up right now, the southern magnetic field is in the northern part of the world. Which sounds strange and unintuitive, it's just the way it's set up right now. That magnetic south is actually in the northern hemisphere. And this actually does change over time. So right now, we have magnetic south not exactly in line with the axis of the Earth, it's a little bit offset. It's about, I think, 11-ish degrees off from the actual northern, like, geographic pole. So, it being magnetic south at the North Pole doesn't really change anything for us. We don't really use the Earth's magnetic field for anything, but some animals do. So animals have adapted, those that use the magnetic field, things like birds. Some birds use the magnetic field to orient themselves towards the magnetic south, which is in the northern hemisphere in the North Pole. And that's how they navigate, essentially. They head towards that just like you would with a compass. But I did mention one thing, and that was that the poles can reverse. And this has happened many, many, many times over Earth's long history, that north and south will flip magnetically on Earth. So right now we have magnetic south in the North Pole. It used to be that the northern magnetic field was in the north, and it fluctuates back and forth every, like, couple million years. And why does it do that? Well, that has to do with essentially how this field is generated. So within the Earth, we know we have the different layers of the core, these molten metals that are just flowing around. All of these metals moving around and flowing do generate a magnetic field. And depending on how those metals are flowing, it's going to essentially make the magnetic field generate in different ways. So right now it's flowing in such a way that magnetic south is pointing towards the north. Eventually that flow will change, causing over thousands of years, the poles will flip. And now you'll have magnetic south in the south and magnetic north in the north. This will eventually happen again. Cosmically, on like a cosmic time scale, it's going to happen pretty soon based on past history. Probably in the next several tens of thousands of years, we're due for one at this point. So we have some history of this that we can see, that even within like normal time scales for us, like decades, or even like hundreds of years, the Earth's magnetic poles are moving. And we're looking here at the South Pole, or magnetic north. It shifted across Antarctica over each 50-year span. It does still move. But for most of our things that we deal with, like compasses, it still generally points north. It's not pointing exactly the same way over decades and decades and decades. But for most of us, it doesn't really affect us. For like scientific instruments where you need to have a precise location of this pole, where it shifting can cause problems, you need to keep closer track of it. You need to keep checking on where it is. So that was magnetic north. Here's magnetic south in the North Pole. It also, over a much longer time period here, we're talking from the 50s all the way back to 600, it has this long, meandering, giant path that it takes. Or even if we look in the bottom right-hand corner over more time scale from us, from what it looks to be 1934-ish up to 2007, it still moves over what for us seems like massive distances. But it's actually not that bad over like a universal time scale. Key takeaway, the poles do move. It's normal. It's due to how the parts of the core are flowing around each other, parts of the mantle. And that's all there is to that. So magnetic poles, those ones I were talking about earlier, they're similar to electric charges in a couple ways. First, they exert forces on each other. This is something we're all abundantly familiar with. You have two sides of a south magnet pointing towards each other. You can feel them repelling away from each other. You can feel them exerted forces. You can feel them pulling towards each other, depending on how you have them set up. They also both attract and repel without touching. These are forces that act at a distance. Things that we've mostly talked about in this class have been contact forces, friction, pushes, pulls, things like that, ropes pulling on things. Those are all contact forces. Electricity and magnetism are what we call field forces. These act at a distance. They don't need to physically touch to have their effects happen. And they also follow the inverse square law, just like gravitation does. Remember, the inverse square law, all that is that we have some parts of the equation, like G m1, m2 over r squared for gravity, like this. This r squared in the denominator, the bigger that denominator gets, the smaller the overall ratio becomes. If I have 1 over 1 squared, that's just 1. If I have 1 over 10 squared, well, now we're at 1 over... I cannot do mental math, and now I look like a fool. Yeah, it's just 100. 1 over 100. So we go from 1, increase it by a factor of 10, now we're 100 times smaller. This is, remember, just this, all the inverse square law is. I should have gotten rid of that. We'll leave that there. So, a couple other things. We're almost done with this. They are different from electric charges in a couple ways as well. Electric charges can be isolated. You can pull an electron away from an atom and just have a pure negative charge. There's no positive side to that, it's just a negative charge. You cannot do that with magnetism. You cannot just pull off and get a negative magnetic field. There will always be a negative side and a positive side to magnetic fields. Remember, when we're splitting those magnets down the middle, you can't just have a negative magnet. You have a positive side and a negative side, a north and a south. So, in a lot of these pictures, if I scroll backwards a bit, in some of the... I'm not going to try that. In some of the pictures we've had pop up, there are these weird field lines around the magnets. These just essentially show the path the magnetic field where that force is acting. It'll always flow from north to south. That's how these fields flow. Just like an electric field would surround every particle, magnetic fields surround every magnet. And we usually will show these off by these lines. If we were in class, which unfortunately we still are not, this is something we can physically do. We can take some iron shavings, which are magnetic, and we can sprinkle them around magnets and then pound on the table to make them spread out, and they can show us these field lines physically. And that's what these demonstrations here are showing. When we have these bar magnets, we can take this powdered metal and it will physically show us these field lines. And eventually they'll all flow towards one end of the magnet and they'll produce something like that. But when these are drawn, they're drawn very much like this. They will all flow outwards away from north, and they will go take the fastest path they can to the south magnet, depending on how far away they are. Like if we look here in the middle, these are very short field lines going from north to south. But when we're all the way here on the end, it's going to have to essentially go all the way around like this to get to the southern pole. So here are some characteristics. We've got, they leave magnets to the north, they travel through the air in a curve. These are things I've been saying. The closer these lines are together, the more of them there are. Like if we have an area that has just one line, it's a very weak magnetic field. But if there's a lot of them really close together, it's going to be a stronger area of magnetic field. And it's always going to be north to south. They will point away from north to south. So, now we can get to calculating these things. The way we show magnetic field in equations is the letter B. Why? I don't know. But we use the letter B for magnetic fields. And the unit for magnetic fields is measured in Teslas, which is shown as a T. So if I have a 100 Tesla magnetic field, I would show that as 100 T, 100 Teslas. Just like we have for distances, 100 meters, we have time, 1 second, we have masses, 1 kilogram. The unit for magnetic fields is a Tesla, shown as a T. Here's another example of Earth's magnetic field. We have the south magnetic pole in the north. Here it's denoted as the, air quotes, north magnetic pole for us, but still at the bottom it does say that the north magnetic pole is in fact the southern magnetic pole. It just depends on how you want to colloquially refer to them. But whenever we're drawing them, even here, the northern magnetic pole should be in the southern hemisphere, in the southern pole. All these lines here, they are flowing away from the south, which in this case is the north magnetic field for Earth, flowing all the way around to the southern magnetic field, which is in the north. Yes, it's confusing, yes, it's weird, but this is just how this era of human history, of Earth's history rather, happened to shake out, that we have some things that are just weird. So we just have some more examples here of electric field lines flowing from north to south. Even for something like a bar magnet, they flow in the same way that they do for Earth, just over a much smaller area. But you have these same field lines, leaving north, heading to south. So, a moving charge entering a magnetic field experiences a force. If we have a magnetic field and we put an electric charge going through it, it's going to feel a force. Just like when we had an electric charge entering an electric field experiencing a force, the same thing happens with magnets. So before, we had the electric field equals the force experienced by the particle divided by the charge of that particle. This is what we now have for magnetic fields, that the force experienced by that particle, F, will be equal to the charge of that particle, Q, times the velocity of the particle, times the magnetic field. F is force, Q is charge, V is velocity, and B is magnetic field strength, measured in Teslas. This is on your formula sheet. F equals QVB. Very straightforward. And we will have some examples to go through. These are very simple. So this is one way to do it. There's also another way. Now if we have a charge moving through a magnetic field, as we're describing here, charges usually aren't just flowing just straight through the air through a magnetic field. They're generally flowing through something, usually through a wire. So if instead we have a current-carrying wire that's going to be going through a magnetic field, it's going to feel a force. So for example here, if we have a current flowing through a wire through the middle of a magnetic field, shown by these two bar magnets, there's going to be a force on that wire. Now, how can we determine which way that force is going to go? The way we can tell which way this force is going to go before we even look at the equation is something called the right-hand rule. So here's what you do essentially. Here we have the current flowing into the wire, into the page. The way you would want to do the right-hand rule is take your hand and just spread it out flat, like it's on a table, spread it flat. Your thumb should be pointing in the direction of the current. So in this case, your thumb should be pointing towards your screen, whatever you have right now, pointing towards your screen. Then you want to curl your hand into a fist. Whichever way your hand is curling is the way the force is going to be going. So in this case, it's going into the page, so the force would curl downwards, the force would be downwards. If you flip your hand over, so now your thumb is pointing away from your screen, in this case, which way would your fingers curl, up or down? They would curl up if it was flowing out of the screen. But in this case, we're flowing into the screen, so that force is downwards. So how do we actually calculate it? Also very simple. In this case, it's just the force times the magnetic field times the current times the length of the wire that's in the magnetic field. So F is that force that's experienced, B would be that magnetic field strength, I is the current in the wire, measured in amps, and L is the length of the wire in meters. And in this case here, it's just this part of the wire here that I have marked off with red. That's the part that's in the magnetic field. That's the part we're going to use. Now this wire could go out like a meter on each side, let's say, and let's say this is a 1 meter gap in the middle, there's 1 meter on the outside, and 1 meter on the other outside, you're not going to use 3 meters. You're going to use the 1 meter that's in the magnetic field. So we're not going to care about the parts outside the magnetic field, just the part inside the field. That's what we care about. The length of the wire inside the magnetic field. Let's do some examples then. So, here's the first one we have here. We have a proton speeding through something called a synchrotron magnetic field generator at 3 times 10 to the 7 meters per second, experiencing a magnetic field of 4 Teslas that is produced by steering magnets inside the machine. We want to find what the magnetic force on that proton is. That's a lot of information just being thrown at you. It sounds like a lot of information, but it's not. Remember, write down your givens. Always write your givens down first. So first thing we're told there is the velocity. So we can write down our velocity is 3 times 10 to the 7th meters per second. They also told us we have a magnetic field of 4 Teslas. So I can put that in for my B, my magnetic field. I put in 4 Teslas. I'm also then told that I just have a charge. I'm not told what that charge is. It's probably going to, if it's just a single charge, remember, protons and electrons have the same charge, so we can just put in the charge of a single proton or a single electron. Remember, we're not going to put in the plus or minus for this. We just put in the value of the charge, which remember is on the back of your formula sheet. It will tell you the charge of an electron is negative 1.6 times 10 to the negative 19. We don't care about that first negative because we don't care if it's positive or negative, so we'll just put 1.6 times 10 to the negative 19. In for that Q. It's on the back of your formula sheet at the top where it says constants. And we're looking for 4, so we write down F equals we don't know. Okay, I have all this information. Now I need to look at my formula sheet and figure out what am I going to use. So I'm going to go over to the part for magnetism, and I have 2 different magnetic forces. One with Q, V, and B, and one with B, I, and L. Well, I have Q, V, and B written down, so I'm going to use that one. I'm going to have that force is equal to QVB. You plug in those numbers. And I want to emphasize again, when you're plugging in things that are exponential, put brackets around them like this. If you don't put brackets around them, your calculator is not going to do what you think it's going to do. You might be entering it in, you think it's fine, but the calculator's not reading it that way. You have to put brackets around those exponentials. So it's treating that entire exponential as a variable, essentially, as one thing, and not 1.6 times 10 minus 19 times 3, doing order of operations entirely incorrectly. Put brackets around every single exponential. So if you just treat each exponential as a variable, like an x like that, put it in brackets, the whole thing. Not the entire equation. Don't put brackets on the entire equation like that and think that'll be fine. Around each part. This first one will be x. This next one here would be y. And then we have 4 over here. It's not an exponential, so I can just put 4. Just put 4. Put brackets around your exponentials like that. Around your scientific notation. Put it around them. Alright, let's get rid of those. There's a bunch of red dots everywhere. But we can just go ahead and plug that into our calculator. And we find we get a force of 1.9 times 10 to the negative 11 newtons. All these are very straightforward. The next 2 I'm going to do, I'm pulling straight from the homework assignment this week. So there we go. Those of you that are actually listening to these. Alright, let's go through this. So, we have Chris. He's hunting in the Northwest Territories up in Canada. And the magnetic field at that point, we're told, is 7 times 10 to the negative 5 Teslas. I'm going to go ahead and write that down before I do anything else. So, the magnetic field, B, is going to be 7, I'm going to use E instead of times 10, 7e to the negative 5 Teslas. Okay, remember, E just is a placeholder for times 10 to the power of. If that's weird to you, just use 7 times 10 to the negative 5th power. E replaces that times 10 to the power of. Makes it easier to punch into the calculator. Alright, we have that. So, he shoots by mistake a duck decoy, and his rubber bullet that he's using acquires a charge of 2 times 10 to the negative 12 coulombs. Alright, that's charge. I can write that down. Q equals 2e to the negative 12 coulombs. Alright, have that written down. And it leaves his gun velocity of 300 meters per second. Alright, and I want to find the magnitude of the magnetic force. That's an F. Alright, so I now have these things. Let's go to my period. Not period. It is early. Let's go to my formula sheet and see what I have there. Well, I don't have I or L, so I'm not going to use that equation. So I'm going to use F equals QVB. F equals QVB. Just like this. Alright, so now I'm going to go ahead and plug these in. Force is going to be equal to 7... I'll do them in order. My Q here is 2e negative 12. My V is 300. And my magnetic field is 7e to the negative 5, like that. 7e negative 5. Alright, now I'm going to go ahead and plug this in my calculator here. I know it tells us the answer, but it's always good just to double check. Make sure we're doing this properly. 2e negative 12 in brackets times 300 times 7e negative 5 in brackets, and we get exactly what we'd expect. We get that the force here is going to be 4.2 e to the negative 14. Exactly what we expect. These are very straightforward. Let's do one more. Another type. We have a wire carrying 10 amps at 90 degrees from the direction of the magnetic field. I'm going to stop right there. It's telling us the angle is 90 degrees. We are not going to really worry about the angle. We're not going to give you magnetic fields or wires going through magnetic fields at weird angles, or you need to find the components. We're not doing that. Every wire will be 90 degrees. So we don't have to worry about it. If it tells us a degree, do not worry about it. If you'd like to go ahead and do some extending of your own to figure out what we'd have to do for that, just like always, we do sine or cosine, depending on the part we need to find, and we'll plug that in. But we're not going to worry about that. If it's 90 degrees, we ignore it. So I'm told we have a current, that's an I, so that would be 10 amps, just like that. 90 degrees, not going to worry about it, through a magnetic field. If the magnitude of the magnetic force, not magnetic field, magnetic force, that's my force, that would be 15 newtons. The magnetic force on 5 meters of length is 15 newtons. Don't write down that magnetic force as 5. It's not. It's 15. Make sure you're paying attention. So we're told 5 meter length. Well, that's my length. That will be 5 meters. What is the strength of the magnetic field? That is B. Okay? So let's go over to my equation sheet. I'm going to use F equals BIL. Alright? So, in this case, I'm not looking for F. I know that. I'm going to rearrange the equation. So I need to get B by itself. So just like always, we need to isolate it. We're going to get everything away from it. If we want to get rid of that I and that L, we do the opposite of what's being done to it. They're all being multiplied together, so we'll just divide IL from both sides. So that will give us F divided by I times L, I'll put them in brackets, equals B. Now B is by itself, now I can solve for B. Let's plug in our information. Our force is 15 newtons. We won't include that. 15 newtons divided by 10 amps multiplied by the length, which is 5. Let's go ahead and plug this into our calculator. We're going to take 15 and divide this by 10 times 5. And we get that our B, our magnetic field, is going to be equal to 0.3 Teslas, which is exactly what we were expecting. And this goes for all of them. All these problems, the circuit ones are maybe a little more difficult because you have to draw a picture. But all these are just straightforward. Write down your givens, pick the equation that matches, and plug in. And that's all there is so far to magnetism for us. We'll go a little bit further next time, but we're not going to talk about that right now. That'll be next week. So if you have any questions, again, please do not hesitate to email me, reach out to me. I'll get back to you as quickly as I can. But otherwise, I hope all of us are still holding up all right while this continues to go on. Hopefully we can come back before the end of the year, but we'll see what happens. All right, I hope you all have a great day.